Greetings, I'm Paul Bamberg, and this is the first in a set of 12 videos that will cover the highlights of Euclidean and non-Euclidean geometry. The non-Euclidean geometries I will cover are spherical geometry, the geometry of the Earth's surface, which is easy to visualize, hyperbolic geometry, which was invented in the early 19th century, and Minkowskian geometry, the geometry of Einstein's special theory of relativity that was invented late in the 19th century. I will focus on the connection between Euclidean geometry and these various non-Euclidean geometries. Each of these videos is accompanied by an R script, and I encourage you, after watching the video, to go through the R scripts. You'll notice that these R scripts generated most of the diagrams that I've included in the videos, and they give you a chance to do numerical calculations that would be very tedious to present in a video, and also to try changing some of the numbers, some of the equations, and see what happens. Since Euclid's geometry is based on his famous 5 postulates, I want to begin by a discussion of the general issue of axioms and their role in mathematics. Euclid begins by defining terms that are fundamental to geometry, like point, line, and right angle. He assumed that his readers were familiar with these concepts, but at the time, it may not have been obvious what Greek words he was going to use to describe them. After making his definitions, he then presents 5 geometric postulates and 5 or 9, depending on which edition you use, so-called common notions. You will see these statements and you will regard them as obvious. One of the postulates basically says you can use a straight edge to draw a line through 2 points, or you can use your compass to draw a circle with a center at a specified point and some other point on its circumference. Having done that, Euclid then goes on and states and proves a very large number of propositions, and in each case the proposition's truth follows from the postulates or from previously proved propositions. Almost always the proposition is accompanied by a geometric diagram, and most of the time if you look at the diagram and look at what Euclid is trying to prove, you will be fairly well convinced by the diagram alone. But his words stand on their own. You don't really need the diagrams in order to accept the truth of Euclid's elements. Now, a more modern view of axioms is that they're statements about entities that are given names. The names may be familiar words or they may be invented words, and we just assume that these axioms are true and try to figure out what we can conclude having assumed their truth. So let me give you a set of axioms that you've been familiar with since you were in elementary school and middle school. These are the axioms for a so-called field. A field has a set of elements and 2 operations. The 2 operations are almost invariably called addition and multiplication, and these have to obey the following set of 9 axioms. First, addition is commutative. If you're adding A to B, you can do it in either order. Second, addition is associative. If you're adding A, B, and C together, you can begin by adding A to B, or you can begin by adding B to C. Or more generally, if you've got a lot of things that you're adding together, you can put the parentheses wherever you like, and it doesn't make any difference. There's an additive identity, whose name is 0, that backwards capital E is read there exists, and the upside down capital A is read for all. So this says there exists an element of the field called 0 with the property that for any element in the field, A is an arbitrary element, if you add 0 to A, either putting 0 on the left or on the right, you get back what you started with. In other words, adding 0 to something doesn't change it. Next says that for every element in the field, there's an additive inverse. It's usually denoted by A with a minus sign in front of it, and its important property is that if you add minus A and A in either order, you get back 0. Next, multiplication, like addition, is associative. If you're multiplying together A, B, and C, you can start by multiplying A and B, or you can start by multiplying B and C. When you're multiplying lots of things, put the parentheses wherever you like. Furthermore, multiplication, like addition, is commutative. The order does not matter. And just as there's an additive identity, there's a multiplicative identity whose name is 1. In every field there exists this quantity 1 with the property that for any element A in the field, 1 times A is equal to A. We're almost done. Axiom 8 says, with the sole exception of 0, every element of the field has a multiplicative inverse. That is, for any A in the field, there exists a multiplicative inverse, A with the exponent minus 1, with the property that when you multiply A inverse by A, you get back 1. And finally, there's a distributive law. A times the sum of B and C is equal to AB plus AC. Now let me introduce the concept of a model for a set of axioms. A model is a set of real-world objects. They might be geometrical objects like lines and squares. They might be arithmetic objects like real numbers or the fractions, the rational numbers. Or they might be things in a computer program. But they're things that you can actually work with. And a model for a set of axioms is a set of objects that satisfies all the axioms. You probably already noticed if A and B are rational numbers, if they are fractions, all those axioms I just stated to you are satisfied. If you're doing the purest of pure mathematics, you don't really need models. But most of us find them reassuring. And in Euclid's Elements, the diagrams will provide models that illustrate what's going on. In the accompanying R scripts, various functions and objects in a computer program will carry out the role of objects in a model. So here are some models for the field axioms. The first one is the set of rational numbers, fractions in lowest terms. In a field, if you add together A and B, you get another element of the field. And when you learned how to add fractions back in late elementary school, basically what you were doing was showing that the rational numbers are closed under the operation of addition. When you learned to multiply fractions, you found out that the rational numbers are closed under the operation of multiplication. When you moved on a year or so later to decimals and accepted the idea that a decimal could have as many digits after the decimal point as you like, you were very close to working with the field of real numbers. And adding and multiplying decimals showed you how to implement the fact that these real numbers are closed under addition and multiplication. Finally, in 8th or 9th grade, you learned about the complex numbers. And one of the things about complex numbers that almost everyone remembers is that if you have a complex number in the denominator, like this 2 plus I, and you don't want it in the denominator, you take the complex number with the 2 plus I in the denominator and multiply by 1 in the form of the complex conjugate divided by itself. And when you multiply things out in the denominator, you get just a plain old real number, no imaginary part. And so this shows that if you divide anything by 2 plus I, the result is another complex number. That means that the axiom that every complex number except 0 has a multiplicative inverse is also satisfied. Here are some less familiar models for a field. The field has to contain 0 and 1. And if I include no other elements, but add the extra rule that 1 plus 1 equals 0, you can check that all of the axioms are satisfied. If you've studied linear algebra, you learned that in general, multiplication of matrices is not commutative. But if you take matrices where the elements on the main diagonal are equal, those on the off diagonal are equal and opposite, you'll discover that those matrices satisfy all the axioms for a field. In fact, they behave exactly like the complex numbers. This matrix is equivalent to the complex number that we call A plus B times I. There are a couple of reasons that it's worth looking at models. When we have a set of axioms, there are two things that could go wrong. One is the axioms might be redundant. Maybe on this list of axioms are things that we don't need to assume are true independently because they follow from the other axioms. More troubling is the possibility that our set of axioms has an inconsistency, that using the axioms we can prove both that something is true and that something is false. Here's where models come in handy. If there's an internal contradiction in a set of axioms, which may well not be apparent, that same contradiction is going to show up in any model that satisfies the axioms, and usually in the model the contradiction will be quite apparent. With Euclid's 5 postulates, it turns out, no one was quite sure for a couple of thousand years whether his 5th postulate about parallel lines could be proved from the other ones. Well, if you have a redundant axiom like that, then in any model that satisfies all the axioms except the one that you think is redundant, the redundant axiom must also be satisfied. In the case of fields, it turns out if you merely assume that axioms 2 through 9 are satisfied, you can prove that axiom 1 is satisfied. And that means, among other things, you can invent a scheme in which all the axioms except the commutativity of multiplication are satisfied. Such a system is known as the system of quaternions. But don't try to invent a scheme where all the axioms except the commutativity of addition are satisfied, because if all the other axioms are satisfied, you can prove that addition is commutative. So, if an axiom is truly independent of the other axioms, it's not a theorem that can be proved from the other axioms, then since the axiom doesn't follow as a consequence of the others, it should be possible to construct a model in which all the axioms except this axiom A are satisfied. And in this course, you're going to meet two geometries, spherical geometry and hyperbolic geometry, in which Euclid's first 4 postulates are satisfied, but the 5th postulate is not satisfied. And this is how mathematicians finally concluded that the 5th postulate could not be proved as a theorem. Now, if you can prove a theorem using nothing but your set of axioms, then it must also be true in any model that satisfies those axioms. And if we consider the system of axioms consisting of the first four of Euclid's postulates, ignoring the one about parallel lines, we'll discover these are valid in spherical geometry and in hyperbolic geometry. I will show this very thoroughly in later videos. And that means that the first 26 propositions in Euclid's Elements, which never use the fifth postulate, are valid for these other geometries. There's a minor exception with proposition 16, where the axiom that you can extend a line as far as you like is not satisfied. So, Euclid unknowingly proved a lot of theorems that turned out to be valid in a form of geometry, hyperbolic geometry, that was not invented until a couple of thousand years after his death. Now let me say a little bit about definitions. The view of modern mathematics is it's impossible to make a definition about the objects you're describing in your axioms. In effect, the objects are described by the axioms. The axioms say they have certain properties. However, the definitions in Euclid are going to be very useful for us because while we're familiar with the concept of a point, it's news to us until we read Euclid's definitions that the Greek word semeion, which means signal flag, same root as in semaphore, is the word that Euclid uses for a point. That the word that refers to the concept of a line, not necessarily a straight one, is the same word that in Greek means stroke or scratch. And that a side of a triangle is specified by the Greek word that's also used for rib. And when Euclid makes postulates about right angles and circles, when he says, you can draw a circle given any center and any radius, these are meaningful only because his definitions have told us the properties of a right angle and of a circle, so we can recognize that his statements are true about the right angles and circles that we're familiar with. Euclid's common notions are axioms, just like his postulates, but they are not specifically geometrical. They apply throughout mathematics. The first of them, for example, is things that are equal to the same thing are also equal to each other. And that's just as important in algebra as it is in geometry. The textbook that we will be using for Euclid's Elements has only 5 of these common notions, but 4 of them got added later, and in the online version of the text you'll find that there are 9 of them. So, here are these postulates, and I'm going to state them the way they're usually presented in geometry courses today. The first one says 2 distinct points determine a unique straight line, and the way you draw that straight line is you put your straight edge down so the 2 points are along the straight edge, and then run your pencil along the straight edge and create a line. How long is a line? It's as long as you like. If you have only part of a line, only a straight line segment, Euclid says you can extend it as far as you like in either direction. Euclid also says you can draw a circle given a center and a specified point on its circumference. We know how to do this in Euclidean geometry by using an ordinary pencil compass. When we get to non-Euclidean geometries, circles will exist, but they won't be as intuitively obvious as Euclidean circles. And we'll have to say, yes, this is a circle because every point on it is at the same distance from the center. The next axiom says all right angles are equal, where a right angle is defined by the property that if two lines cross at a right angle, the angle on either side of the crossing point is equal. And finally, the modern version of the fifth postulate is if you have a straight line and choose a point, let's call it P, not on the line, then there is one and only one line through P that fails to intersect L, and that's called the line through P that's parallel to L. This is not the way Euclid stated his fifth postulate, but it's the one that is best known. Now, as I said, we're going to be using the R scripting language. In this language, it's very easy to carry out precisely the operations with points, lines, circles, and other objects that are mentioned in geometry, and to display them graphically. So I can give you a function that draws the line between A and B and permits you to extend it in either direction if you like. I can give you a function that draws a circle with a specified center and a specified point on its circumference. And what I will be doing in the next 4 of these R scripts is to show that the models created by these computer scripts are all consistent with Euclid's first 4 postulates, but that only Euclid's postulates, the ones that define Euclidean geometry, are consistent with his fifth postulate. So that'll be enough to get you started. In the next video, I will get in detail into Euclidean geometry and show you a set of tools for drawing diagrams in R that are consistent with all of Euclid's postulates.